My name is Mовсисян Oganес. The presentation is improvement of productivity of fuzzing through interval mutations. In today's world, development of reliable software is a very important aspect in information technologies. Fuzzing is one of the most popular and effective methodologies of dynamic analysis. So, fuzzing is a program the mistakes found in a program and the general operations of fuzzing look like this. First step, the input is generated. Next step is running the program on this data. And step 3, analysis of the launch of the program, verify behavior. And then the first step again. There are a lot of instruments of fuzzing instruments. For instance, AFL is one of the most popular fuzzers. WinAFL is a modified version of AFL for fuzzing for Windows. KFL fuzzer for the core of OS. Syscaller also fuzzer for OS cores. ISP-fuzzer is an enhanced fuzzing framework. But all these instruments have one drawback, and they cannot use information on the structure of the input data. Here we show general scheme of ISP fuzzers. In green is the plugins that were developed for solving our task for our program. In ISP fuzzer there is mutation fuzzer, mutation plugin, but they do not use information on the structure of input data. They look at the random mutations, and they easily can change these mutations in important parts of input data. What do we mean saying important parts of input data? For instance, first 4 bytes ELF file has the following value, 07F ELF, and if we have a program that works with CLF files, then probably it will stop its operations if it gets incorrect ELFI at the beginning. When we want to test this program through fuzzing, we need to generate correct ELF files. And the task of our work is to find what intervals of input data impact doing execution of specific basic blocks. Then apply mutation for all intervals of input data that do not impact at specific basic blocks. To tackle this task, we implemented 3 main plugins. First, trace generation. The next plugin is the one solving what parts, deciding what parts of input data will influence basic blocks execution, and the last part, interval mutation. Here we show general scheme of operations for plugins developed. Let's look at all of them one by one. So generation, trace generation. Dynamo is a system of instruments for code when it is execution. With this instrument, through fuzzing, when the program is working, we can add assemblers instructions for every basic block, and thus, when executing, we have all the addresses of basic blocks that are executed. And the sequence of these basic blocks will be the trace of execution of the program. Zero-cost dynamic symbolic execution is a plugin that was developed to solve the following task: to understand what parts of input data influence execution of specific basic blocks. General algorithm of this plugin is in 2 parts. First part is selecting interesting basic blocks, and part number 2, bringing the basic blocks together with the intervals of input data. Interesting basic block selection. So we acknowledge them interesting if they are part of at least P% advantage of all traces, and also clients can develop their own metrics for selecting interesting basic blocks. After we've selected interesting basic blocks, we need to link them with the input data. If we imagine a program that works with the CLF files, and the part of the program where it is checked where input file is a correct ELF file. If we have two sets of input data, and the first byte of which equals to 7f, then obviously in this program, in this function, second part of the operator will work in two cases. So the program execution traces of execution will contain the same basic block that correlates with the second part of the operator if. And what do? We take all input data that correlate to the traces that contain selected basic blocks and bring these sets of data together. And we assume that this overlap is the part that impacts the execution of the selected basic block. And also another important point is that if the overlap is empty, then we stop processing this basic block because nothing can be said about this basic block, what the input data impacts it. We just stop the processing. And now, when we have already found what parts of input data impacts the execution of the basic block, we fix these values in the input data, and the remaining parts. In the remaining parts, we will accept the mutations, and that's how we have new input data. And the strategy of interval mutations. Interval mutations, if are on if at the x execution at least no y no y execution was done, and this can be done through configuration file. So the results are we tested programs through ordinary fuzzing and fuzzing with interval mutations. From the table you can see that only two programs we have negative results. In the rest we found more paths in the program, and we also found bugs in the program that were checked manually. Any questions? So, okay, I have a question about defining the paths, the traces. I don't really understand what do you mean by the number of the traces you cover. You know, that last table. I mentioned that we are doing instrumentation of programs, and the sequence of basic blocks of which were operating when program was executed, and we call it trace of execution of a program. And this is the path of the program, of how it works. So in my understanding, the number of basic blocks, not the number, but the sequence of specific basic blocks. If we take all sequences, then a large volume should be accumulated. We are tackling this problem. We do not accumulate all sequences. We save trace if it contains a lot of basic blocks. If there are replicas, if the program has already been going this way, this trace, we do not store it. And the cycles, we do not store them if... and that's why traces are not so large, but they do not... they are not compatible with the definition. So it means that you cut some of the cycles. Yes, if a program, for instance, has an unlimited cycle, you should not store this. That was my question all about. So it looked unrealistic. Very good question. Thank you. So this 5% of traces, was it defined empirically, or you have statistics saying that more than 5%, okay, we take it? I'd say why we need this metrics at all, why this limitation. For instance, let's imagine that one basic block is contained by two various traces, but the overlap of input data correlating with these traces doesn't impact execution of this basic block, but just an incidental overlap. We will spend much resource on that, on processing this basic block. But if the percentage is large, then the probability is high that the overlapping of input data really impacts the execution of this basic block. Thank you. Could you please switch to slide 1 or 3, where you compare fuzzers? Yes, this one. The right column is fuzzer, user's input structure information. So, what do you mean is fuzzer does not use input structure information? In ISP fuzzer, there is an opportunity like that to use information on the structure and articulate data according to the structure. We mean standard mutation of ISP fuzzer, standard mutation that is random and doesn't use such information. Just to clarify, this is just about mutation. Yes? Thank you. Actually, the same question about syscaller, because it has a definition of specification of input data it actively uses. That's why we wanted to clarify this table. Well, probably you should clarify it in the table what you mean. I don't understand the question then. Following the previous question, I was also doubtful. Syscaller allows you to specify the types of input data for system calls, file descriptor and how the structure looks like. So there is special language of specification for this. And if you just look at this table, then it's a huge question mark. Why in this bar it stays, why no in syscaller? As far as I know, syscaller doesn't use such information. But we can say that the majority of fuzzers do not use such information. Okay, fine, then we can discuss it offline. And let's move on according to our agenda. Thank you very much.